So our goal in 9.3 and 9.4 will be to take our 6 trig functions from our unit circle and then graph them as their own separate standalone functions in the x and y plane that we usually work with. We're going to start out with just looking at sine and cosine in 9.3, and we're going to look at transforming them and so on. But the first thing we want to note is when we talk about our trig functions or our circular functions, they're what we call periodic. So when we say a function is periodic, that just means the y values will repeat on regular intervals. Formally in function notation, this is what it looks like. So remember, f of x in a function is just your y value. So it's saying if we put this x value in, we're going to get back a y value. And it's going to be equal to a y value where we take x plus some quantity n times p. Here, n is just going to be any integer, and p is going to be some fixed real number. So it just says on these regular intervals, these y values are going to be the same. So sine and cosine, they're periodic functions, and in fact, all the 6 trig functions are periodic. But sine and cosine, they have a period of 2 pi. So their period is 2 pi because if you pick any point, so you go any arc length, well, let's just go to pi over 3. So if I've gone this arc length of pi over 3, I end up at the point 1/2 square root 3 over 2, where the 1/2 would be the cosine of pi over 3, and the square root 3 over 2 would be the sine of pi over 3. But imagine that we go around, from this point, we go around a distance of 2 pi. So a distance of 2 pi is one complete rotation. So if I've gone a distance of 2 pi, if I've added 2 pi, then I'm back at the same point. I could go in the opposite direction as well. I could go in the opposite direction, 2 pi, and I would still end up at the same point, where cosine is half, sine is square root 3 over 2. So that's why the period is 2 pi. Let's just look at our sine value. So if we look at sine, and here we're putting in an arc length into our function. I'm going to put parentheses around so it's consistent with our function notation. So I put in an arc length into sine. It's going to give me some value. And that value will be equal to whatever that arc length was, plus any integer n times the period, which is 2 pi. So for example, if we did look at sine of pi over 3, it's going to be equal to sine of pi over 3 plus any integer times 2 pi. So go any distance 2 pi around, you're back to that same value. Well, our goal here is to not use variables like s. Because we want to take these trig functions and put them into our x and y plane, instead of putting an arc length s into our function, this distance, did we go along the unit circle? Do we typically use s for? We're going to let s be equal to our x value in the xy plane. So if I go a distance arc length s of pi over 3, that is now going to be my x value of pi over 3 that I put into my, in this case, we're looking at sine. So sine of x instead of s is going to give me back some value. And here we're going to do our traditional values, which would be a y value. So put in an x, get back a y. And same for cosine. If you look at the cosine function, instead of putting in an arc length of s, our arc length is going to be the x value that we put in, and then we'll get back this y value. These are the functions that we're going to graph in the xy plane. Always keep in mind that the x that we're putting in is that distance along the unit circle, and that y value is going to be the x value on the unit circle for cosine, the y value on the unit circle for sine. Let's go ahead and graph sine first. So again, function f of x is going to be sine of x, or in other words, f of x is equal to y, so y is equal to sine of x. I'm going to start out with just looking at points. The first points are going to be in the first quadrant, and then I'll just do the generic x and y axis points on the unit circle. So for example, we're going to start out with x value of 0, so that's an arc length of 0. So sine of 0 is going to be 0. At pi over 6, the sine value is 1/2. And I'm leaving a little bit of space, and I'll show you why in just a second. At pi over 4, sine is square root 2 over 2. But I want to graph that, so I'm going to approximate this in my calculator to 1 decimal place, and it comes out at approximately 0.7. It's hard for me to guesstimate where square root of 2 over 2 lies. And then at pi over 3, sine is going to be square root 3 over 2. Again, if I put that in my calculator, I get a 0.9. So going back to the 1/2, decimal representation is 0.5. So this is an easy way to remember the half square root 2 over 2 square root 3 over 2 is that, look, it's 0.5, 0.7, 0.9. They're odd numbers, 5, 7, 9. Okay? So we start out at 0, we go 0.5, 0.7, 0.9, and then at pi over 2, the sine function is 1. And then I'm not going to do those intermediate values in quadrants 2, 3, and 4. I'm just going to jump to our x-axis, the next point on the x-axis of the unit circle, which would be pi. Sine of pi is 0. And then we'll jump to the 3 pi over 2. Sine there is going to be -1. And then at 2 pi, we've gone full circle and we're back at 0. Let's go ahead and translate these values onto our coordinate system where we have our x-axis and our y-axis. So if we look at 0, sine of 0 is 0. Where's pi over 6 though? So you see on the axes, I've just labeled the key x, y axis values on the unit circle, which would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. So if I was going to look for pi over 6, well, I know the halfway point between 0 and pi over 2 would be pi over 4. So again, just looking at the unit circle. And then the pi over 6 and the pi over 3, it cuts up that first quadrant into thirds. So if you kind of look at the distance from 0 to pi over 2, you can look at that as being the first quadrant on the unit circle. So if we just sort of guesstimate where the thirds would be, I would have a pi over 6 and a pi over 3 on either side. So at pi over 6, we have half. So let me go ahead and label my y-axis. Instead of calling that first tick point 1, maybe I'll go up 2 and call that 1. And then -1 below. So that way I could see that half would be that halfway point. Pi over 4 is 0.7, so a little bit more than a half. Pi over 3 is 0.9, so we're almost at 1. And then pi over 2 is 1. It's this nice arc, which makes sense if you look at the unit circle and how it arcs along. So that would be our sine values, first quadrant, start at 0, goes to 1. Now from pi over 2 to pi, we're looking at quadrant 2 of our unit circle. And I'm not going to go ahead and do all those 3 pi over 4 and all those little intermediate values. Instead, I'm just going to remember that the values are all going to be the same, except for we may differ from negative and positive. So if I come back down to 0 at pi, I know I'm going to mirror the same shape. And you could put in those values. You could just put them in a calculator. Just make sure that you're in radians. put in the next value after pi over 2 on our unit circle would be 2 pi over 3. So if you do sine of 2 pi over 3 in radians, you should get that that's about 0.9. So these values are going to mirror each other. It'll go 0.9, 0.7, 0.5, and 0 at pi. Now from pi to 3 pi over 2, we're in third quadrant, sine is negative. At 3 pi over 2, we're going to get down to negative 1. And again, I'm just mirroring that curve from 0 to negative 1. 2 pi is 0. We're going to come back up. So look at what we did. From 0 to pi, this corresponds with the sine values in quadrants 1 and 2 on the unit circle. And I'm going to go back up to that unit circle. And you see we have that same arch coming around. It goes from 0 to 1, and then from 1 to 0. And then you could see from pi to 2 pi, those are our negative sine values, just looking at the sine values. We're going from 0 to negative 1, and negative 1 back up to 0. So these graphs should make sense. Let's try the negative side. So if you look at the value from 0 to negative pi over 2, that's actually going to correspond to the fourth quadrant on the unit circle because we're going in the opposite direction. We're going clockwise. And in that case, sine starts at 0, and at negative pi over 2, that corresponds to the same value as 3 pi over 2. That would be negative 1. So again, we're just arching around. Negative pi, sine is 0. At negative 3 pi over 2, that corresponds to a positive pi over 2. So we're at 1. And then a negative 2 pi, we're back at 0. And that's our sine function. And you see that the pattern repeats. So every interval of 2 pi, you get the same y values. Typically, we call the values from 0 to 2 pi, those x values, typically that's where we'll put 1 period. But it really doesn't matter. It doesn't matter what value you start at. As long as you go a distance of 2 pi, you've gone 1 complete period, meaning you've gotten all the positive and negative values, and you've got all the values of increasing, decreasing, of going up and down, and then the pattern will repeat. Going up to the top, we can now talk about some of these properties that we have with our sine function, and we talked about this before. So the domain is going to be all real numbers, so negative to positive infinity. Again, if you look at the graph in the xy plane, you could see that although I didn't put arrows at the end, I can, because our pattern will continue on and continue on. So we have all the x values. We could put anything into our function. But notice that the range, the y values, and we talked about this prior, the y values just go from negative 1 to positive 1, including the negative 1 and the positive 1. Something interesting, and this is going to become important when we start graphing, is that sine is what we call an odd function. So recall the properties of odd functions. It says if the negative is on the outside, it's the same as if you had the negative on the inside of the function. This is going to be important because when you have a negative on your x value, that would be a reflection about the y-axis. But since sine is a negative or odd function, we can actually take that negative out from the inside. So from the argument, we can bring it out to the front of sine. But with all of our trig functions, they're either going to be even or odd. And in all cases, we can either cancel the negative that's in the argument, or we could bring it out if it's in the argument, which means that we will never have to graph a reflection about the y-axis. So like our prior transformations, where we could have a reflection about the y and also a reflection about the x-axis, with all of our trig functions, we can only have at most a reflection about the x-axis. So no reflection about the y-axis. That's actually good news. And the period here is 2 pi. No matter where you start in this graph, like let's just say I started at negative pi. If I go a distance of 2 pi, I would be at positive pi. That's one period. I've gotten all my negative and positive values, and then the pattern starts to repeat again. Let's do the same thing with the cosine function. So again, we're just going to get all the values in the first quadrant, and then we're just going to look at those key points. Pi over 2, pi, 3 pi over 2, 2 pi, and then the negative values as well. Looking at cosine, if I were on the unit circle and I put an arc length of 0 in, cosine is going to be 1. If I put in pi over 6, I'll get square root 3 over 2. And we already did these values with sine. So we know that's 0.9. At pi over 4, I get square root 2 over 2, which I know is 0.7, or approximately. And then at pi over 3, cosine is half. So that would be 0.5. Pi over 2, we have 0. And then we'll skip down to pi, where cosine is negative 1. 3 pi over 2 is 0. 2 pi is 1. So where sine started out at 0, 0, the origin, cosine, on the other hand, starts out at 0, and I'll label 2 tick marks as 1, and then I'll have a negative 1. Cosine starts out at the point 0, 1 when we're looking at the xy plane. And then at pi over 6, so again, remember we have a pi over 4 halfway between 0 and pi over 2. And then we split up that interval into thirds. First value we hit is pi over 6. And then we get to pi over 3. So at pi over 6, 0.9, so really close. Pi over 4, 0.7. Pi over 3, half. Pi over 2, 0. Same curve, same arc as with the sine function, because it's the same circle that we're taking these values from. But instead of going from 0 to 1, we're going from 1 to 0. And then we'll skip over to pi. At pi, cosine is negative 1. So again, same curve from 0 to negative 1. 3 pi over 2, we're back at 0. And at 2 pi, we're at 1. Cosine and sine have the same graph, they're just shifted. Okay? Imagine if we were to take this cosine graph and we would shift it over pi over 2 to the right, we would actually be looking at our sine graph. Now if we go in the opposite direction, the negative pi over 2 corresponds to 3 pi over 2, cosine is 0. So we're coming back down. At negative pi, cosine is negative 1. Negative 3 pi over 2, that corresponds to pi over 2. Cosine is going to be 0. And at negative 2 pi, we're back at 1. So exact same graph as sine, just shifted over. It starts at 1 and goes down. Sine starts at 0 and goes up. And in fact, maybe I will graph them together. So this is our going on forever. This would be cosine. And go on forever. Here, let me just go ahead and quickly sketch sine. 0, 1, 0, negative 1, 0. And you see how fast I'm doing this, because those key values are the only ones you actually need, and then you just have to remember the curvature. So at negative pi over 2, we're back at negative 1. We go up to 0. And then we're up at 1, back down to 0. So it's nice to see these side by side. And to see that if I just shift sine pi over 2 to the left or cosine pi over 2 to the right, then they will be exactly the same. Okay, so let's just talk about the values that we have up here for our cosine function. Again, similar to the sine function, can put any value in there, any x value, but the range only from -1 to 1. Okay. It's an even function. So if we look at cosine, if we put in a negative x value, it's going to be the same as cosine of a positive x value, which is good news, because whenever you have a negative multiplied onto your x value, you can just get rid of it. When you have the negative on the x, remember what that's saying. It's saying whether I have a negative or a positive x, my y values are going to be the same. So if we look at that graphically, what that's telling us is that, let's look at the blue curve, and let's look at pi over 3. If we look at the value here for positive pi over 3, and then you go to negative pi over 3, you have the same y values. It's a reflection about the y-axis. Imagine folding along the y-axis. Cosine matches up perfectly. It doesn't matter whether the x is negative or positive, still going to be the same y value, so we don't ever have to worry about that negative in the argument. We can just cancel it. Super nice. And again, like sine, it has a period of 2 pi. So although traditionally, if we were going to graph one period of cosine, we would do the same thing. We would start at 0 and we'd go to 2 pi. But you don't have to. As long as you've gone a distance of 2 pi, you can graph your period anywhere you want. So why do we always go from 0 to 2 pi? For one, positive values or x values are easy to work with. And two, when we think about applying our trig functions to the real world, and imagine this as being like sine waves. Look at this with radio signals, things like that, satellite signals. It has this curvature wave, a trig function. When we apply it in real life, typically the x-axis stands for time, and then the y-axis will stand for something else, like an impulse, right? Decibels, maybe, if you're looking at sound. So over time, what's happening to those decibels? Are they going up or are they going down? But typically time starts at 0. We don't care about the negative values when we're doing it in real world applications, which is why typically whenever we graph one period of a trig function, we include the origin because that makes more sense. The next thing we're going to do, now that we've seen the basic graph of sine and cosine, is we're going to transform them. The first thing that we're going to talk about is what we call amplitude. Now, amplitude is simply the vertical stretch or shrink that we had when we were looking at other functions from Math 135. We would shrink it down towards the x-axis or would stretch it out from the x-axis. A vertical stretch or shrink with sine and cosine is called amplitude. The word amplitude only applies to sine and cosine, not the other four trig functions, because when we talk about amplitude, we're talking about the maximum value, y value, and the minimum. So what is the highest amplitude? In the case of sine and cosine, their highest value is 1. And then their lowest value is -1. So the amplitude would go from +1 to -1. With the other trig functions, and we'll see this when we look at 9.4, they don't have a minimum or a maximum value, so we really don't use the word amplitude. So when we talk about amplitude, that's going to be a number multiplied outside our trig function. So it would be, for sine, some a value, we usually use a for amplitude, times our sine, or some a value times our cosine. So the amplitude, when we look at that value, a, we're only looking at the positive. So if it was like a -2 on the outside, we ignore the negative. Amplitude would just be 2. And then, of course, it can't be 0, or else we wouldn't have the sine or the cosine function. Let's go ahead and graph just sine. We'll do an example here where we're looking at our regular sine function and comparing it to 2 times sine or 1/2 times sine so we could see what happens with our amplitude. Something to note is when we are talking about amplitude, that is on the outside of our trig function after sine cosine has done its job. Put in an x, we either get our sine or our cosine value. So that a value is changing your y value, not your x value. So whenever we change the y value, it does exactly what we think we should do. If it's a +2, a number greater than 1, it's going to stretch it out to larger values. If it's a value that's less than 1, like half, it should shrink it in towards the x-axis. So let's see if that's actually what happens when we plot some points. And I'm only going to do the key points 0, pi over 2 pi, 3 pi over 2, and 2 pi, because it has a nice periodic graph that doesn't change, so we really don't need those intermediate values. Looking at just our regular sine function, we have 0, 1, 0, -1, 0. Now, when we multiply by 2, we're just multiplying these 0, 1, 0, -1, 0 by 2. Since sine of x is 0, if I multiply it by 2, it's still going to be 0. Sine of x, when we put in pi over 2, sine of pi over 2 is 1. Multiply by 2, we get 2. If we put in pi, we have 0, so times 2 is still going to be 0. Sine of 3 pi over 2 is -1, times 2 is going to be a -2. And then 2 pi would be 0, times 2 is still 0. So notice that whenever we have a 0 value, that doesn't change because an amplitude is multiplying the value of the function. So if the value of the function is 0, no change. If we were going to look at the last one where we have 1/2 sine x, it's going to be 0. 1/2 times sine of pi over 2 is 1, so 1/2 times 1 is going to be 1/2. 0, -1/2, and 0. So I'm going to go ahead and just look at basically the positive side of the graph and maybe just go to negative pi over 2 so we can kind of see how the pattern will continue. The tick mark, I'm going to do as I did before. 2 up would be my 1, and then 2 more, I'm going to call that 2. So then I'm going to have 2 down would be a -1 and a -2, and you don't have to use that scale. You could do every tick mark is like 1, 2, 3, and so on. I'm going to graph in different colors. So I'll start out with blue. Our sine of x passes through 0. It goes to 1, 0, -1, 0. Such a nice function. If I was going to go the other way at negative pi over 2, I'd be at -1. And that would be our sine x equal to y. Let's go green. So 2 sine of x is going to pass through 0. Pi over 2 is going to be 2, 0, then -2, 0. It did exactly what I thought it would do. It's stretching it up. And then at -2 at negative pi over 2. So that's going to be our sine, 2 sine of x. Okay, red. 0, 1/2, 0, -1/2, 0. So it did exactly what I thought it would do. It's shrinking it down. So that's going to be 1/2. Oops, that doesn't look good. 1/2 sine x. That's my y value there. Okay, so that's amplitude. And amplitude is really easy to graph because technically all I had to do was, instead of using 1 and -1, if my amplitude is 2, I just label on my axis 2 and -2 and graph our sine or cosine function in the same shape it was. So just a note, remember that you can always check your graphs in an online graphing program such as Desmos. They're going to be very helpful when you're looking at transformations. The next set of transformations we're going to talk about is what we call a period. And we already talked about that period before. Remember, sine cosine has a period of 2 pi. The period just says, okay, give me a distance on the x-axis where we have one full cycle of our function or one full period of our function. And sometimes, if in the case where you're multiplying the x value by some value, so if we look at y equal to sine of b times x or y equal to cosine of b times x, whenever you multiply your x value by some value, what you're doing is you're changing the period. So remember that whenever we change our x value, it kind of does the opposite of what we think we're going to do. So if we're multiplying x by some value b, it'll change the period from 2 pi to 2 pi divided by b. So multiplying x by b means the period will change by divide by b. And this would correspond to, in our prior transformations, as a horizontal stretch or shrink. So what that's going to do is, if we shrink our period, then it's going to shrink the graph in towards the y-axis. If we stretch our period out and make it larger, then that's going to stretch our graph out from the y-axis. So we're either shrinking in or stretching out from our y-axis. In example 1, we want to graph y equal to the sine of 1/3 x. First of all, I notice that I have the 1/3 times x. So I know that that's going to be my b value. And I'm changing my period. So this period is going to be equal to the normal period of sine is 2 pi. If I divide it by the b value of 1/3, that's the same as 2 pi times 3. So it's going to give me 6 pi. So in this case, I'm actually stretching it out from the normal period of 2 pi to a period of 6 pi. So I'm not going to go ahead and graph all these values from 0 to pi over 2 to pi, 3 pi over 2, 2 pi, and then keep going all the way up to 6 pi. Remember that the graph of sine and cosine, it's in fours. Think about the quadrant 1, 2, 3, 4. We have 4 values, 4 key values on our axis. So I'm going to stay with that. I know that no matter what, the graph will always look the same. For sine, it will start at the 0, 0. It'll go up, come back down, go down, come back up. That's just the way the graph is. So to graph, I'm just going to go 1, 2, 3, 4. And instead of calling this 2 pi, I'm just going to call it 6 pi because that's my new period. And if I go in the opposite direction, 1, 2, 3, 4, I'm at -6 pi. And that's it. So to graph a change in period, like to graph a change of amplitude, you just relabel the y-axis. If the amplitude is 2, you go from 2 to -2 instead of 1 to -1. Simple. To change the period on your graph, instead of writing 2 pi and -2 pi, in this case, our new period is 6 pi. So 6 pi, -6 pi, but still going to break it up into 4 pieces because the graph is still going to start at 0, 0, go up, down, up. So half of 6 pi would be 3 pi. So I just have to figure out what these new values are. And notice you could put 3 pi in for x, 1/3 times 3 pi. The 3's cancel, and that's sine of pi, which is what we normally would have at that. Between 0 and 3 pi, that's going to be half of 3 pi. So that's 3 pi over 2. There's an easy way to figure out how you would label your axes. What you do is you take your new period which is 6 pi. And you know that you have to divide it into fourths. So you just divide it into 4. And if I were to reduce that, I would have 3 pi over 2. What that tells us is that each one of these intervals is a length of 3 pi over 2. So I've gone 1 3 pi over 2, 2 3 pi over 2, which would be 3 pi, 3 times 3 pi over 2, which would be 9 pi over 2, and then 4 times 3 pi over 2 gives me 12 pi over 2, which would be pi over 6. So here, this is what I mean. I'll do this off to the side. The first distance was 3 pi over 2. And then the next point would be 2 times 3 pi over 2. So you see that 6 pi over 2, or the 2's canceling. You see that's our 3 pi. Then the 9 pi over 2, that was going a distance of 3 of these 3 pi over 2, which would give us the 9 pi over 2. And then the last one, the 6 pi, we've gone a distance of 4 of these 3 pi over 2's, which would be 12 pi over 2, or 6 pi. So again, change in period, write down the new period, break it into 4, and then label the other 3. Now, if I go into the negative direction, it's just going to be the same values, but now negative. Negative 3 pi over 2. Negative 3 pi. Negative 9 pi over 2. Notice that there's nothing multiplied in the front of the sine function, so the amplitude is the same. It's still going to be 1 and negative 1. My graph? Simple. Sine starts at 0, it goes up to 1, goes back down to 0, negative 1, 0. And graph. Easy. And then if I look at the negative direction, goes down to negative 1, up to 0, positive 1, 0. And we are done. And we've actually graphed 2 periods. So what do you have to label if you're hand graphing? Well, you have to label those 4 key points on the axis if you're graphing just one period. If you're doing more than one period, just remember to graph those key points on the x-axis. And then on the y-axis, you would have your amplitude. Try another one. In example 2, we want to graph cosine of 3 over 2 times x. I see that 3 over 2, which would be my b value. So now my period has changed. It's going to be 2 pi over 3 over 2. So that's 2 pi times 2 over 3, which would be 4 pi over 3. Same thing. I'm going 1, 2, 3, 4. New period is 4 pi over 3. If I'm going in the negative direction, I'm going 1, 2, 3, 4, negative 4 pi over 3. The amplitude didn't change. I know it's going to be 1 and negative 1. But if it did change, I would just relabel it. If it was 2 times cosine of 3 halves x, I would just, instead of doing 1 negative 1, I would do 2 negative 2. So really easy. And remember, shape's not going to change. It's still going to start at 1, go down to 0, then negative 1, 0, positive 1. We just have to figure out what these other tick marks are. So we have to take this period of 4 pi over 3. We're dividing it by 4. So remember, if you divide it by 4, or 4 over 1, that's the same as taking 4 pi over 3 times 1/4. Here I could see that the 4's will cancel, and each one of those intervals is going to be a distance of pi over 3. So I know in this first interval, I've gone a distance of 1 pi over 3, 2 pi over 3 for the next one. This becomes 3 pi over 3, which I could reduce, right, and simplify that to just pi. And then the last one is 4 pi over 3. So makes sense. Same values on the other side. We've gone a negative pi over 3, negative 2 pi over 3, negative 3 pi over 3, which would be a negative pi, and then negative 4 pi over 3. Cosine starts at 1, goes down to 0, negative 1, 0, positive 1. And then on the negative side, goes down to 0, negative 1, 0, positive 1. And that is it. Let's go ahead and put these two ideas together and graph transformations where we combine both amplitude and period. In example 3, we have y equal to 2 times sine of 3/4 x. So I can see that I'm changing my period with that 3/4, and I'm changing my amplitude with the 2 on the outside. So I know that I have a b value is 3/4. That would be a change in period. My period is going to be equal to, the normal period is 2 pi, and I'm dividing it by 3/4. So that's going to be 2 pi times 4/3, which would give me 8 pi over 3. And I also see that this 2 on the outside, that would be my amplitude, is equal to 2. So this is how I'm going to set this up. I'm going to go, okay, amplitude is 2. So I know I have to go from 2 to negative 2. That's how I would label my y-axis. That's not really a nice scale. That's going to irritate me. I went up really high, so they don't match that well. And I also know I have to go to a period of 8 pi over 3. So I'm going to go out 1, 2, 3, 4, 8 pi over 3. This is the sine function. So I'm going to start at 0, go up to 2, 0, down to negative 2, and then back to 0. Again, if I were also graphing on the negative side, then I would be going to negative 8 pi over 3. Okay, so I just have to figure out what these marks are. I'm taking 8 pi over 3. I'm dividing it by 4, which is the same as multiplying by 1/4. So reduce by 4 top and bottom, it looks like it's going to be 2 pi over 3. So this first distance is the distance of 2 pi over 3. And then I'm going to go, so that's 1 pi over 3, or 2 pi over 3. Maybe I'll write it out. 1 times 2 pi over 3, which is 2 pi over 3. And then I'm going to go 2 of these 2 pi over 3s, which would give me 4 pi over 3. And then I'm going to go 3 of these 2 pi over 3s, which would give me 6 pi over 3, or 2 pi. And then I've already got that 4, 2 pi over 3, which was my 8 pi. So the label on my axis is going to be 2 pi over 3, 4 pi over 3, 6 pi over 3, which becomes 2 pi, and then the 8 pi over 3. The negative values are going to be mirrored. So negative 2 pi over 3, negative 4 pi over 3, negative 2 pi. And I'm done labeling my axes. Since this is the sine function, I start at 0, go up, back down to 0, go down, up to 0, and I'm done. So really nice when we have change of period and amplitude. The graph stays exactly the same. You're just relabeling the axes. Again, on the negative side, we're going to go down to -2 to 0, up +2, 0. And that's it. Oh, that's a sad graph. Good enough. Just a sketch. Let's look at example 4. Example 4, changed it just a little bit. Notice that we have the 2 times x, so I know this is going to be a change of period. And then the 1/2 in front means it's going to be a change in amplitude. But now we have this negative. So the negative is going to be a reflection about the x-axis, because once we put in a value for x, we have cosine of 2x. Function has done its job. We're going to multiply by half. That's going to change the amplitude. So that final negative in the front, that's going to say, okay, if your y value is positive, you're going to make it negative. If the y value is negative, you're going to make it positive. So in this case, we're going to graph, I'm going to do it in 2 stages. I'm going to graph period amplitude, as I usually do, just changing my axes, the labels on my axis, and just graph our normal cosine function. But then once I graph the normal cosine function, I'm going to actually do the reflection. Let me write down all the transformations. So remember, the amplitude is always positive. We don't include the negative. So here my amplitude is going to be equal to 1/2. So that tells me it's going to shrink in, right? It's going to be a vertical shrink towards the x-axis. My period is going to change. It's 2 pi over 2. So now my period is pi. But that negative in the front means I'm also going to be reflecting. So reflect across the x-axis. So let's do our period amplitude first, and I'll do a light sketch of that, and maybe I'll change color for my final graph. As we normally do, we label the axis. The amplitude is now half. So I'm going to just do a positive half and a negative half. Period is pi. 1, 2, 3, 4, pi. 1, 2, 3, 4, negative pi. Filling in those intermediate values. Again, if you take pi and divide by 4, it's just pi over 4. So each one of these is going to be a distance of pi over 4. So I've gone 1 pi over 4. 2 pi over 4 will reduce to pi over 2. 3 pi over 4. And then 4 pi over 4 would be the pi. Corresponding negative values, negative pi over 4, negative pi over 2, negative 3 pi over 4. And this is cosine, so it's going to start at the 1/2. It's going to go down. What I'm going to do is I'm going to go ahead and maybe I'll just do the points. I'm not going to do the reflection yet. I'm going to just do the regular 1/2 cosine of 2x. So it starts at half, goes to 0 at pi over 4, goes to negative half at pi over 2, back up, and ends. Maybe I'll just do like a sort of slashy one. So it's clear that this is not my final graph, even though I use black for my final graph. Then we go down to 0, negative half, back up to 0. I don't know if you can hear the crazy chickens in my yard. They're very loud. Okay, so that is actually y equal to 1/2 cosine of 2x. Now my reflection, so I'll just go ahead and use black for my final graph. It's going to take any positive values. So if I'm at a positive 1/2, I'm going to bring that down to a negative 1/2. And maybe I'll just take away this black because I don't want it to be black. The zeros are going to stay where they are because remember the reflection is across the x-axis. So if you're at 0, that's going to stay. All the zeros are going to stay where they are. Just the positive values come down to negative. The negative values will come back up to positive. So this 1 at pi, we have a positive 1/2. It's going to come down to a negative 1/2. Okay. So again, the zeros stay the same. If it's a negative 1, it comes up, or a negative 1/2, it comes back up to positive. And if it's positive, it goes down to negative. So this would be the graph y equal to negative 1/2 cosine of 2x. So we've done a amplitude, which would be a stretch vertically or a shrink. We have done the period change, which would be a horizontal shrink or stretch. And now we've also looked at reflections across the x-axis. The final transformation that we're going to look at is, we actually have 2 more, is going to be those shifts that go left, right, up, and down. When we shift left and right, that's what we call a phase shift. And these were in Math 135, shifts left, right, up, and down. These were called translations. So now we're going to look at our translations for our trig functions, which would be our horizontal and vertical shifts. So when we talk about a horizontal shift and we're looking at our trig or circular functions, these are what we call phase shifts. So that would be shifting along the x-axis. There is no name for a shift up down. It's still just a vertical shift. In example 5, we're going to graph y equal to the cosine of, in parentheses, x plus pi over 6. So notice that x plus pi over 6, that plus pi over 6 is going to be our shift. So in this case, going back to transformations prior, remember that whenever we add to the x value, it's not going to be a shift right, it's actually a shift left because we're doing opposite of what we think we should do. So if I'm adding pi over 6, that's actually going to be a shift left by pi over 6 units. Okay, so in the case where we rename that as a phase shift, instead of calling it a horizontal shift left, when we talk about a phase shift, if it's a plus pi over 6 and we know we're going to shift left, then the phase shift is going to be negative because it's saying we're going to go in a negative direction pi over 6 units. In the case, if it's an x minus some value, it would be a shift right. So the phase shift would actually be positive so that we understand that we're going to shift positive direction, whatever units it is. Now, to me, the phase shifts are the most difficult because you have to start with your normal, breaking everything up into 4. In this case, we're looking at cosine. And I haven't even, so we're looking at cosine. We're going to break it up into 4s, but then we have to take that graph of cosine and shift it over. What I'm going to do is I'm going to start as usual. And in this case, this is the only transformation. So I know I'm going to do a negative 1 and a positive 1. And I'm going to break up into 4s. So 2 pi, and negative 2 pi. However, I'm going to have to take and shift my graph. Let's go ahead and do our normal values of pi over 2, pi, 3 pi over 2, negative pi over 2, negative pi, negative 3 pi over 2. Cosine, we start at 1, 0, negative 1, 0, 1. Maybe I should have done it with dashed, but that's okay. And then we come down the other way. So here we have our normal cosine function. And now when I shift pi over 6 to the left, what I'm going to do is I'm going to take this whole graph and go left pi over 6. So imagine that moving left pi over 6, we're going to subtract, which is why our phase shift is a minus. We're going to minus pi over 6 from each one of these key values. So let's see, 2 pi minus pi over 6. I have to change this to 12 pi over 6. So I have a common denominator. That means I'm going to be at 11 pi over 6. And you could look at the unit circle as well. So this value is what I really want to label. That would be 11 pi over 6. This is now going to be my value 1. It shifted over pi over 6. So this whole graph is going to do a shift left of pi over 6. I'm just going to go ahead and sketch the graph, and then I'll worry about relabeling my axes with these new values. So again, maybe it's easier to start at where we were at the top. We were at 1, we went to 0, and then we went to negative 1, and then back up to 0, and then positive 1. Down to 0, then to negative 1, back up to 0, and then to 1. So again, I've just shifted my graph. What are these points on the axis? Well, you just have to minus pi over 6 from each one of those original values. So if we look at 3 pi over 2 and we subtract pi over 6, it's going to be 9 pi over 6 minus pi over 6. That would give me 8 pi over 6. So that's going to have to be reduced to 4 pi over 3. Because you do have to have these new values on your axes, if your graph is getting kind of messy, you can label these new values above, or actually near the point if you want to. So this would be a 4 pi over 3 if it's getting a little bit crowded. And then you think about taking the next value, pi minus pi over 6. But let's see if we can recognize a pattern first. We started out at 11 pi over 6, and then we went to 8 pi over 6, which if you just look at the numerator, and the denominator is the same, if you look at the numerator, we took away 3. So if I keep that pattern going from 8 minus 3, I should get 5 pi over 6. Let's see, because remember, there's a pattern to all of this with our trig functions. That's what makes them so nice. So if I'm at pi, would be my next point, and I subtract pi over 6, then this becomes 6 pi over 6 minus pi over 6. And that's 5 pi over 6. It's doing exactly what I think it should do. So again, let's look at that pattern. Numerator is reducing by 3, 11 to 8 to 5. So the next one must be 2 pi over 6, which in turn would change to pi over 3. And then here we have a negative pi over 6. If we kept that pattern going, just imagine 5 pi over 6, take away 3, we're at 2 pi over 6. I'll write the pattern down here. We were at 11 pi over 6, and then we went to 8 pi over 6 and reduced. Then we went to 5 pi over 6, minus 3 would be 2 pi over 6. Oops, do I want to reduce would be pi over 3, sorry. And then we went to, if we were still continuing this process to the negative direction, if we're minusing 3 from 2, it would be a negative 1 pi over 6, which gave us that negative pi over 6. And if we continue with that 3, this idea of 3, it would be negative 3 pi over 6. And that should reduce, oops, sorry, it's not negative 3. I'm subtracting 3. So if I'm at negative 1 pi over 6, negative 1 minus 3 would be negative 4 pi over 6. Minus 3 would be negative 7 pi over 6. Minus 3 would be negative 10 pi over 6. I think that's sufficient. So negative pi over 6, the next value would be negative 4 pi over 6, again because we're minusing, which would reduce to negative 2 pi over 3. Maybe I'll put this above. And then the negative 7 pi over 6. The next value should be the negative 10 pi over 6. Oh, I have to go one more. But that will reduce. And then it'll be negative 13 pi over 6 would be the last one. So this is an easy one to stick in. And then the negative 10 pi over 6 would be negative 5 pi over 3. Where am I going to put that? Negative 5 pi over 3. Crazy. So the idea is that you have to shift it over either left or right, but don't forget to label the new values so it's clear what your shift is, because sketching a graph by hand, sometimes it's not clear, right? There's a very subtle difference sometimes in the shift. So you do have to label stuff. Let's look at one where we have a minus. So sine of x minus pi over 4. There's no change in period or amplitude. We just have that minus pi over 4. So that would be a phase shift. And since it's a minus, we're actually going to go right. So if we're going right, we're going in the positive direction. Our phase shift is a positive pi over 4. And that just means that once we've broken up our axis, our x-axis, we would be adding pi over 4 to each one of our key values. So just as a reminder, this is going to be right. Pi over 4. I'm going to go ahead, and amplitude didn't change, so I'm still doing a 1 and a negative 1. Still going to go 1, 2, 3, 4, end up at 2 pi, 1, 2, 3, 4, end up at negative 2 pi. And then maybe I'll sketch my original sign that starts at 0, and then it's going to go up to 1. Do I want to put in all those values? Because I'm just going to have to mess up my axes. Yeah, I'll put them in. So this was pi over 2, pi, 3 pi over 2. Negative pi over 2, negative pi, negative 3 pi over 2. And sine goes 0, 1, 0, -1, 0. So again, this is not the transformation. So negative goes to 0, -1 comes back up. We go, there we go. Okay, now I'm going to do my shift. I'm going to start at 2 pi, and in this case, I'm going to go to the right pi over 4. When you look at pi over 4, that's actually a really nice shift because look at the 0 point. From 0 to pi over 2, pi over 4 is a halfway point. So basically what we're doing is, I'll start at the negative pi over 2. We're just moving everything to the right, and in this case it's halfway between each one of these intervals. So where we had our 0, it's now to the right here at pi over 4. And then where we had the 1, and then we have our 0, and then we have our -1, and then we're back up at 0. So here, -1, 0, +1, 0. And we have our shift. We just have to label our axis. So this would be pi over 4. So that's 1 pi over 4, 2, 3 pi over 4. And these values are fairly simple because we're adding 3 to our numerator, or we're going by 3. So 1 pi over 4, 3 pi over 4. This should be a 5 pi over 4. Maybe I'll write it above. And then we have 7 pi over 4. And 9 pi over 4. Okay. 1, 3, 5, 7, 9. Great. So this becomes a negative pi over 4. Maybe I should have put it above. -1, -3. So it matches up really nicely. So -5 and -7. Okay, let me double check. Yes. Yep, that all looks good. So again, the difficulty here, in my opinion, is just the relabeling of it, being able to shift left or right and redraw your graph. That, to me, that's not the issue. It's more figuring out what those key values are on the x-axis. Now, you're not going to be responsible on an exam or even in the homework of doing many transformations in one function. However, you will be responsible on an exam for being able to write a function in the correct order and then identify all the transformations. So in example 7, we have these two trig functions, and these are just a mess. But our goal here is to, if you look at the box above, is to be able to write it in the form of, if we're looking at the sine function, if there's some c value, we want to have it plus a sine of b times, in parentheses, x minus d. So all that's saying is that if there is a value multiplied by the x, you want to factor that value out. So that would be that b value. You want to make sure you factor that value out because that b value will affect your period, but more importantly, It's so that you can correctly identify your phase shift. The phase shift is just adding or subtracting from only the x value. So anything multiplied by that x, like a negative or a 2 or something, that has to be factored out. Also, if there is a negative in front of the b, in the case of sine, it's an odd function, we can bring that negative out in front of the a value, not the c value. So here, this c value at the end here, imagine putting in some value x. You've done all this stuff. You've gone your shift, that minus d. You've changed your period, which was the b. The a value is the amplitude. You've done all of that. That c, that is just affecting the y value. And it's either going to be negative or positive. If it's positive, it's a shift up. If it's negative, it's a shift down. So that would be our last transformation. That would be our shift up and down. But everything else basically is around our function itself. Let's look at the cosine. So you want to get it in the form, same thing, y equal to some shift up or down. That would be your c value, plus or minus. A would be the amplitude. Cosine of b is going to be your period. Factor that out, and the x minus d would be your phase shift. In example 7a, I noticed that there's a 2 times x. That's not in proper form. So my first step would be to factor out that 2. And we would write y equal to 7 minus 3 times cosine. Factor out the 2. And when we factor out the 2, we're factoring out from the 2x and the pi. So remember, when we factor something out, what we're actually doing is dividing every term by, in this case, 2. So we're going to take 2x, we're going to divide it by 2, and that gives us our x. Pi divided by 2 is simply pi over 2. If you're unsure if you factored out that value correctly, try to get rid of the parentheses and multiply the 2 back in. Do you get back to where you started at, which was the 2x plus pi? And the answer is yes. Okay, so we've taken care of that 2 in multiplied by the x. And now everything is actually in the correct form for us to identify all the transformations. When we identify the transformations, it's easiest just to start from the inside. So we'll start with the x plus pi over 2. So the plus pi over 2 is going to be a shift either left or right. Since it's a plus, it's a shift left. So instead of writing shift left pi over 2, we use that language of phase shift. So that's our phase shift. And if we are going left, since we're going in the negative direction, it's a negative pi over 2. Because in reality, what we're doing is minusing pi over 2 by our usual values on the x-axis. And that would give us our shift left. The 2 that we have in front of the parentheses that we factored out, that's going to change our period. So the normal period of cosine is 2 pi. So we divide it by that d value of 2, and now our period is pi. If we ignore that negative, so we're done on the inside. Ignore the minus in front of the 3. All we care about is that 3, because that would be our amplitude. Remember, amplitude is never negative. And in this case, our amplitude would be positive 3. However, we do have that negative. And if there is a negative in front of your amplitude, that negative would indicate a reflection about the x-axis. So here we have reflect across x-axis. And then the last thing that we're going to see is this 7. And it's a positive 7. So since it's a positive 7, you ignore the negative 3 cosine, all that stuff. You just care about the 7. Since it's a positive 7, it's going to be a shift up. All right. So again, not going to graph it. Crazy. You could put this in Desmos though if you want to graph it. So we're not going to graph it. But instead, what we're going to do is just write it in the correct form. And a problem like this will be on your exam. Write it in the correct form and identify the transformations. Let's try this again. Something to remember is cosine is an even function, sine is an odd function. So if there's a negative multiplied by the x value for cosine, you can get rid of it. If you have a negative times the x value, which we do here in B, and it's a sine function, we have to pull it out. But we can't pull it out until we actually factor out that negative 3. I just can't pull that negative out because in the parentheses, the minus 3x plus pi over 4, that's one piece. So if I pull the negative out from the x, I also have to pull a negative out from the pi over 4. Let's go ahead and write this in the correct form. The first thing I'm going to address is that negative 3 times x. I want to get rid of that. So I'm going to keep everything else the same. And I'm going to factor out the negative 3. So that means I'm going to divide everything by negative 3. So the negative 3x divided by negative 3 becomes x. But notice that the plus pi over 4 now becomes a negative. So we're taking the positive pi over 4 and we're dividing it by negative 3. So that's the same as pi over 4 times negative 1/3, which would give us a negative pi over 12 if I did my math correctly. Okay, let me double check. If I was to distribute that negative 3 on the outside, I would have a minus or a negative 3x, and then the negative would turn to a plus, and I would have 3 pi over 12, which would reduce to pi over 4. Okay, all correct. However, I have a negative in front of the 3 here that I have to address. Remember when I said if there's a negative times, you got that negative times, and it's negative times 3. On that x value, you have to get rid of it. Since sine is an odd function, that negative is going to come out in front of the sign. It's not going to affect that minus 4. So think about it as factoring out a negative 1. If I pull that negative and I bring it out in the front, the negative will change to positive. So now I have y equal to negative 4 minus minus becomes plus sine of 3 times x minus pi over 12. Okay, now it's written in the correct form for me to identify all the transformations. Again, I'm going to start with the inner parentheses, the x minus pi over 12. Since it's a minus pi over 12, I know that's going to be a shift right pi over 12 units. And a shift right, that would be my phase shift. So my phase shift is going to be, shifting right means we're going to shift towards the positive direction. It's going to be a positive pi over 12. Again, if I were graphing this, that means I'm just going to add pi over 12 to each one of those values on my x-axis. The next thing I see is I see that 3, which is going to change my period. So now my period is going to be, the normal period is 2 pi for sine, and I'm going to divide it by 3. And since that doesn't reduce, that is my period. Now notice that there is no number multiplied by the sign. So my amplitude did not change. It's still 1. Technically, I don't have to write amplitude of 1 because that is not, it hasn't been transformed. It's still the original value. But if you want to write down that the amplitude is unchanged and it still remains as 1, that's fine. The last thing is going to be that -4. Since it's a -4, so remember, function's done its job. That -4 is just going to change your y value. You're going to be subtracting 4, which means it's going to be a shift down by 4 units. And I would just write shift down 4. Okay, so that is writing it in the correct form and identifying the transformations. Let's look at, in general, the correct order that you should graph. And the only real issue here is number 5. Well, I don't want that. In number 5, that would be the vertical shift up or down. That has to be last. All the other transformations can be completed in any order that you wish. I will typically do period amplitude first because that's just a matter of relabeling my X and Y axis and sketching that initial graph. And then I'll do a phase shift left or right next, and then I'll do my reflection across the x-axis. But really, you could reflect across the x-axis first and then do a shift left or right. It just, for me, it's easier to do my left right, because a reflection across the x-axis just means all the zeros stay where they are, negatives go positive, positive goes negative, not a problem. And then the last always has to be any shift up or down. We're going to just do one graph where we have more than 2 transformations. On an exam, you would have at most 2 transformations, and then we'll stop here. We have y equal to 1 plus sine of -x minus pi over 4. First of all, that's not in the correct form because I see that negative in front of the x that I have to factor out. So if I bring out that negative, parentheses x plus pi over 4. But now I have that negative inside the argument of the sine function, which I can't have. Sine function is odd, so that negative comes out in front. And now this is, I actually don't like having that equal sign there. Too many equal signs. This is now y equal to 1 minus sine of, I don't need the brackets anymore, I just have x plus pi over 4. So it looks like I have the plus pi over 4 is going to be a phase shift of negative pi over 4. We're going to go left pi over 4. And then that negative in front of the sign, that would be a reflector across the x-axis. And then that positive 1 is going to be a shift up 1 unit. Let me write down those transformations so I don't forget them. I have a phase shift of negative pi over 4. Since we're going left, we're minusing pi over 4 from our usual values. And I'm going to reflect across our x-axis. And then the last thing would be that 1, which would be a shift up because it's a positive 1. I have 3 transformations. I'm going to start with, I'm going to do sketches of the transformations, and I'll just have the darkest color be the last one. So let's start with period didn't change, amplitude didn't change. So I could just go ahead and do a 1 and a -1. However, I did have a shift up 1 unit. So if my maximum value was 1, if I shift up, it's now going to be a maximum value of 2. So I know right away I'm going to have to do a 1 and a 2. Because I did change. I did a shift up 1. The reflection across the x-axis, that's not going to change how I label my x-axis, but that phase shift will. I'm going to go ahead and do the 1, 2, 3, 4. 1, 2, 3, 4. My phase shift is pi over 4 to the left, which means I'm going to do a shift halfway, right? Notice I didn't label my initial values. So it's a halfway shift. So my 2 pi value for that sine function is going to be now at that, if I minus pi over 4, it's going to be at that value there. Let's go ahead and let me just go ahead and sketch the original sine function where we start at 0 and we go to 1. Maybe I'll do it like this, and then 0, -1, and 0. And then we go down and up. Okay, so that was my original sine function. I'm going to go ahead and shift it. And I'm going to, maybe I will do a, you know what, I'm going to do red. So when I shift it, this 0 is going to be here. And then it's going to go down to -1. Back up to 0. And then here would be the 1. Down to 0. -1. 0. +1. And 0. That's a little bit weird. Okay, so I did my shift, and I'll worry about labeling the axis later. Now what I'm going to do is I'm going to reflect across the x-axis. So when I reflect across the x-axis, any point that's at 0 will stay. So all these zeros will stay. However, if it's a positive, it becomes negative. And if it's a negative, it becomes +1. And if it's a positive, it becomes negative. Zeros stay. Negative goes to positive. Okay, maybe I'll just do a light green. So this is where I'm at. I've completed my shift and my reflection. The last thing I'm going to do is I'm going to shift up 1. So I'm going to take these values and I'm going to shift them all up 1. Let's see, where would be a good place to start? Well, I guess I'll start here. And the zeros go to 1. 0, oops, that's not quite at 1. So zeros go to 1. The -1 goes to 0. And then the 0 goes to 1. So it looks like that. So let's see, 0 to 1, -1 goes to 0. 0 goes to 1. 1 goes to 2. 0 goes to 1. Okay, so there is my SAD graph where I did all the transformations. We had a shift left, pi over 4. We did a reflection, and then our final shift up. Now, what are the labels on the axis. Well, remember, we're going from 2 pi, we're subtracting, and we did this in a prior one, we're subtracting pi over 4. So that would be 8 pi over 4 minus pi over 4 would give me a 7 pi over 4. So this value here, and it doesn't matter where you label it, you can even label it at the point. This could be 7 pi over 4 if it becomes unclear. Okay, so at this point here, this was 3 pi over 2. Oops, wrong place. This was 3 pi over 2. And we were subtracting pi over 4. So the 3 pi over 2 minus pi over 4 became 6 over 4. And that would be 5 pi over 4. So you see what we're doing, we're reducing that numerator by 2. 7, 5, this should be 3, this should be 1 pi over 4. And then we're going to have to go the other way. This would be a negative. Ooh, where am I going to put that one? This is going to be a now, just right in there. Negative pi over 4. Okay, so we did negative pi over 4. Now we're going to go negative 3 pi over 4. Negative 5 pi over 4. Oops. Oh, that's sad looking. Negative 7 pi over 4. And then this would be a negative 9 pi over 4. Whew. Okay, so again on the exam you'll have at most 2 transformations to graph, and I'm going to stick to sine cosine. In the next section we're going to look at the other functions, but as far as graphing goes, graphing transformations, I'm just going to stick with sine cosine on an exam. However, you will have to have something more complicated to write in a simplified or the correct form as we did in example 7, and then identify those transformations. So this is it for this section.